Go ahead, Srinidhi.
So good evening to one and all present here and welcome to the session. I'm Srinidhi and I'm volunteering with India as a project lead. I would like to use this opportunity to talk a little about Women in Big Data. So Women in Big Data was founded as a grassroots organization in the year 2015 to inspire and connect women in big data and allied careers. In 2020, the organization shifted into a not-for-profit to cultivate opportunities, unblock latent potential, and act as a catalyst for advancement in career for women. Women in Big Data India chapter aims to act as a platform to bridge the divide between industry and academia and to improve women representation in data and its allied fields. To accomplish this goal, we have 5 anchor programs, namely Vidya, Saraswati, Shakti, Gayatri, and Lakshmi, under the able guidance and inputs of a panel of EC members, directors, and experts from both the industry and academia. Currently, Women in Big Data India has chapters across 4 reputed education institutions and 5 industry partners. We have more such collaborations lined up in the near future. For the next element in the agenda, I'd like to introduce our presenter, Mr. Ramdas Menon. Mr. Ramdas is a certified Six Sigma Black Belt and reliability engineer from the American Society for Quality with 29 years of experience in the industry. He completed his bachelor's in chemical engineering at Jadavpur University, Calcutta, followed by an MTech in chemical engineering at IIT Madras. He has worked across several reputed firms, including General Electric, TVS Electronics, and Pfizer, and is currently serving as a managing partner at Ekagra Solutions, which he founded in November 2008. He joined the Women in Big Data team to share his expertise in statistics and effective communication to encourage more and more women to take up careers in STEM. This expert session on relevance of statistical methods today, as the name suggests, aimed to give an overview of the relevance of statistical concepts and methods in today's industry, especially in areas such as quality assurance, designing, and data science. I hope that at the end of this session, you will have a good idea of the importance of statistics in today's world. We will have a Q&A session after the presentation, and the recorded version of the session will be available in our website. And thank you one and all for being here. And now over to Mr. Ramdas. Thank you.
Thank you very much. It is a very succinct introduction. Can we have the screen, please, so that we can start?
Yes, yes. One second.
And Srinidhi, you are going to be moving the slides, right?
Yes, sir. Yeah, that's right.
Right. Go ahead. Let me have a look. Yeah, that's better. I hope the volume is okay. I hope all of you can hear me clearly, right? Just one of you needs to say yes. Srinidhi, you can hear me. Soumya, Samiksha, everyone?
Yes, we can hear you, Ramdas.
Thank you so much. Thank you so much. I can then start without having all these earphones and other paraphernalia. So can we go to the first slide? We can just, the first slide is just the next one. You can just move the slide. Slide 2, yeah. Yeah, you can, this is just agenda. This is what I'm going to cover. Hopefully I should be able to cover everything. And most of what I'm going to talk today is based on the work which I have done both at my tenure in General Electric and the work I've done for several clients. Next slide, please. Okay, next, this is just a header. You can go to the next slide. Yeah. Okay, now you can see this sentence here, statistical thinking will one day be as necessary for efficient citizenship. Today in India, literacy is a big problem. But in the Western world, literacy is not a very big problem. But even there, statistical thinking is something, and we'll look at very, very small examples today to show how statistical thinking is something which it doesn't come very easily to people. Now, guess who said this? Anyone? Does the audience have a chance to unmute themselves and maybe just give a guess? Is that possible here today?
Yes, sir.
Okay, anyone, either the hosts or any of the audience, can somebody take a guess? This is, of course, widely misattributed to somebody. So I just wanted to check if people are aware. Anyway, I just, now that we've started late, maybe I'll go through the slides a bit faster. This is actually misattributed to H.G. Wells. Can you just press enter so that you can go to the next, the animation works. Yeah. This is actually attributed to a very eminent statistician by name Samuel Wilks. And in fact, I've read several books which have misattributed it to A.G. Wells. But the point is, statistical thinking is definitely required. And the fact that statistical thinking is something which is, it is statistical thinking doesn't mean the ability to calculate the mean or the standard deviation. That is not statistical thinking. Statistical thinking is the ability to think reasonably and logically. Can we go to the next slide? Yeah. This is a definition of statistics. It looks quite a mouthful. It deals with the collection, presentation, analysis, and use of data. Many of us, we think that it is only got to do with some kind of analysis. It's got to do with everything. And data for what? Data to make decisions, solve problems, and design products and processes. Next slide, please. This is a very interesting idea. You can see here how statistical thinking has evolved over time. Statistical thinking, of course, H.G. Wells talked about. The actual quote by Wells I've given at the bottom, at the last slide. So H.G. Wells talks something about averages, maxima, minima. He said, just averages are not enough. You have to talk about maximum and minimum. That is one. He was not a statistician, by the way. Then, of course, you had the, I would say, the second decade of the 20th century. That was where a lot of work, you can see here, expectation, concepts of probability, variance, risk. Some of these were already done in the previous century, but people like Ronald Fisher, I'm sure all of you have heard of Fisher, they made a humongous contribution to statistical methods. I'll discuss some of them as we go along. And the last part you can see is statistical thinking. This is where we talk about, visualization and cognition, correlation. These are concepts which are, it's easy to write down formulae and do these, but as we can see in the example which follows, statistical thinking is all this and not quite this. So let's take a look at the next slide where I've asked a question. Yeah, probably. Go ahead. Next one. So all of you are familiar with the game of dice, right? Shakuni of the Mahabharata was very notorious for this. Just go ahead, Srinidhi, you can just, slowly. Not so fast, not so fast, okay. What I wanted to say was, this was a question which I had asked, but Srinidhi, you have already given over the answer. No? So the volcano Vesuvius erupted in 79 CE, and of course, you might be wondering what I'm talking about volcanoes and eruptions when we are talking about statistics. But the point is here, in the fifth point here, dice were discovered in the ruins, and it is claimed that these were loaded. Can anybody tell me the meaning of the word loaded die? What does the word loaded die mean? Anyone? Are people actually here, or have they all put themselves on mute and updating Facebook status? I heard somebody
so
trying
the chance of one side showing up more, it's loaded. So the weight is on one side. So one side would have a higher chance of coming up.
Very good. Who is that?
So Pranav.
Okay. One request, whenever anyone wants to say something, just announce your name, because I have no clue who is speaking. So it makes sense to say your name. You are right. In fact, you gave too elaborate an explanation. A loaded die simply means if you were to toss the die a certain number of times, if it is fair, then there would be an equal chance for any of these numbers to come up. So if it's not so, you will know that it's loaded. But the question is, how will you know that? Next, can you just go ahead a little bit? Yeah. This is the question. Now, how will you check the claim? So let's assume that, you are supposed to get 600. If you toss a die 600 times, then you're supposed to get each of these numbers about 100 times. Now the question is, if one of them is 101 and the other one is 99, will you conclude that the die is biased or not? The question is, how would you actually treat a table of data? And by the way, what I'm saying sounds more difficult than it actually is. By just looking at the data, of the number of falls of 3s and 4s and 5s and 6s. How can you actually check whether it is biased? And you might think this is some kind of an academic discussion. I actually had opportunity to use this concept in deciding a certain company's marketing plans. So all these tools have very high relevance. Next, please. Just keep pressing enter. Yeah. We'll come back to this, as I said, when we look at more examples. Okay, just go ahead slowly, Srinidhi. There are multiplication rules. So I'm not good. This is not a class on probability. Then, of course, you have the Bayes theorem. For those who are interested, I can even give you the link to an article which I wrote on Bayes theorem and COVID. It's slightly painful. Many people might not like it, but just go ahead, Srinidhi. This is a slide where we can, thankfully, we're not going to work out your problem. By the way, can anybody answer this question? What's the probability of getting 3 heads in a row? Anyone? Anyone? If you
3 by 9, sir.
Okay, that's a good answer. I'm not saying it's the right answer. What is the probability of getting 1 head if you flip a coin?
1 by 2.
Very good. So the probability of getting 3 heads is 1 by 2 plus 1 by 2 or into 1 by 2?
Into 1 by 2.
Correct. So it will be 1 by 2 to the power 3. It will be 1 by 8, not 3 by 9. Anyway, just go to the next, please. Now, just think about this question. If you were to flip a coin 100 times and you got, if you flip a coin 100 times, the number of heads expected is how much? Expected.
50.
50 is right. 50 is right. Now the question is, suppose you got 52 heads. Will you say that the coin is biased? I mean, there is something wrong either in the person who's tossing the coin, or as somebody pointed out, the coin is loaded. If you were to get 52 heads, okay, I can see Lija has said no. Okay. Then what about 53 is my answer? 53?
No, sir.
54? Okay, so now the question is, it's very unlikely you will get 50, but let's assume from 50 to 99 or 50 to 100, there is a number between 50 and 100 where you will say enough is enough. Is that part agreed? I mean, will you get 99 heads? I'm just asking you a question. No. Dev Maheshwari has said no. That's right. So now the question is, it's the same question which I asked a short while ago, and the same example which I'll give you a business application towards the end of today's lecture. There is a certain number between 50 and 100. Yeah, okay, Dia Sethi wants to say we might. No. Are you saying we might to my proposal that you might get 99 heads? No. Thank you very much, Khyati. Also, I can see. I'm very happy to see so many people participating. See, theoretically, yes is not really a good enough answer. It's not really a good enough answer. Basically, there's a particular test I'm talking about. If anybody wants to type the name of the test, you can actually type it out. But there is a test. That's a very simple test whereby if you apply that test, you can actually tell whether the number of heads that you have got is no. It's a good answer, Dev Maheshwari. It's a good answer. It's not the t-test. But anyway, we'll come back to this. I have actually given an answer to this towards the end, and we'll discuss that when we come. Go ahead, please, Srinidhi, please start moving the slides. Yeah, as well as cover a similar business. In fact, this business decision-making situation, to tell you the truth, it was an afternoon like this, very hot, and I had had a very good lunch, and I was almost half asleep. And somehow something stirred in my mind, and I was able to ask this question only at the last minute. And people were very upset when we asked this question. So anyway, you will see it. That business situation and this coin situation is exactly the same. The idea of statistical thinking is, can we spot similar situations? That's the catch. Next slide, please. Okay. Now, Srinidhi, you'll have to go maybe every 10-15 seconds, you can just go ahead so that the sentences come out. So this has been modified from the classic example. There's a gentleman by name Daniel Kahneman who got the Nobel Prize in Economics in 2002. He wrote a very interesting book called Thinking Fast and Slow. Probably some of you might have read it. It contains the work done by him and Tversky on the subject of behavioral economics. And the example, of course, I have slightly changed it. The example there, it's called the Linda example. Maybe you can Google and check it out while I would not like you to do it now. But I have sort of adjusted it for Indian conditions. So you can see Vijayan is 35 years old, single, outspoken, very bright. He has a PhD in economics and philosophy. As a student, he was deeply concerned with issues of discrimination and social justice. Now, I'm going to give 3 statements. Your job is, in fact, all of those who have been kind enough to chat with me, you can give the order. Rank these statements in descending order based on likelihood that they are true. In other words, rank the most probable sentence first and the least probable last. So, seriously, just go ahead and then stop. Yeah, put all 3, put 1, 2 more. Yeah. Stop, now stop. So these sentences are Vijayan is active in the communist movement. That's the first sentence. B, Vijayan works in a college as a professor, and Vijayan works in a college and is an active communist. Now, based on the information that I've given you in the 3rd and 4th paragraphs, rank these statements in order of probability. Okay, Khyati, thank you very much. You've been the first off the mark. I'm not going to say whether you are yes or whether you're right or wrong, but BAC. Who said CAB? Somebody said CAB. Okay, Srinidhi. Oh, Srinidhi also answering. Very good. BCA. Very good. Bhavika. Okay. Anushri. BAC. BCA. CAB. Yashika has said CAB. Very interesting answer. Priyanka, a lot of, okay, I'm very, very, very happy to see somebody has said again, Trisha has said CAB. Good. I'm really happy to see this kind of participation. Excellent. Excellent. Very good. Now, I'm not going to comment on, in fact, I'm going to make you people come up with the answer. I'm going to make you people come up with the answer. Okay, before you move the slides, Srinidhi, I want everybody to think, and maybe like you're chatting, Sivang has also said BAC. There are a lot of people with BAC. A couple of people with CAB, CBA, right? Now, Srinidhi, don't advance a slide now. I just want to ask a question to people. Now, how many, or rather look at it this way, will there be more professors in the country or more communists in the country? Yeah, it's somebody, yeah, okay, right. More communists, because a communist movement is a movement that spreads across people. In fact, you will have a lot of, you might have a lot of teachers there. You might, but then you will also have workers there. You will also have people who are in, shall we say, in ordinary jobs, 9-to-5 jobs. There could be so many people who actually believe in these ideas, but they are neither trade union leaders, neither are they professors, but they are all people who subscribe to that one. So the number of communists will always be much higher than the number of professors. It's fairly obvious. So now, Srinidhi, can you move the slide? Yeah, can you move it once again? Yeah. So therefore, the probability that he is a communist is more than, because if you want to look at probability as number of communists divided by total population, and in fact C, many people gave C as the answer. C is actually the intersection of these two, right? I said Vijayan is a communist and a college student. That probability is the lowest. So what I've given you A, B, and C, that is the correct option. That is the correct option. So this is what I meant by statistical thinking. So when you're forced to, when somebody actually holds a gun to your head and forces you to answer questions, then you might, for example, go to the next slide. Srinidhi, can you go to the next slide? Now let's look at, instead of asking the question that way, I asked you this way. You know, there are 100 people answering to Vijayan's description. How many of them could be yes? Go ahead. College professors give a number, college professors and active. So obviously you will always give the second number as lesser than the first. Right? So what I said a short while ago just happened to be true right now, right? In spite of having all the information, people still gave the wrong choices. Next slide, please. Yeah. Distributions and the uses, next slide. Of course, this is a very, very, okay, thank you very much. This is a very popular curve. Everybody knows this. Normal distribution, and many people are actually unable to remember these numbers. It's not a big deal. But what I wanted to tell you is, if somebody asks you, what do you mean by data being normal? What is the meaning? That meaning is what I've tried to put in. When data is normal, it means that about 68%, 68.26, but I put 68.3. About 68% lies between one standard deviation of the mean, and 95, it's actually 95.44. It lies between two standard deviations of the mean, and 99.7 lies between three standard deviations. So that's the meaning of the word. Someone was saying something? Okay, I'll just go ahead. Just go the advance the slide by one. So before you advance the slide, anybody would like to guess the name of the person to whom this distribution is credited? Anyone in the chat? This is named up. Very good. Gauss, Trisha, thank you very much. Of course, there are controversies. So thank you very much. There are controversies about even this little thing. Some people say that Abraham de Moivre actually came up with this, but that's not a. I mean, let's not worry about it. You can go ahead, Srinidhi, just go ahead with the slide. It's widely credited to Carl Gauss, and of course, suppose the mean weight. Okay, I'm taking just a minute or so to explain this concept. Suppose the mean of the adult male population in a country is 65 kgs, and the standard deviation. This is one thing. Just pause it for a minute, Srinidhi. I just wanted to talk about. Yeah, that's a good idea. In fact, a lot of people were giving answers, and I was very happy to see all the answers. And now, there's just one point which I wanted to stress, which I stress to everybody. In fact, today morning I was having a 3-hour session with the engineers and technologists in a very large chemical company based in Bombay. We were looking at project reviews. Many people, whenever they give data, they give only the average. Nobody gives standard deviation. And that is something which I've been trying my level best to convince people, especially if you are going to use data to make decisions. You're going to use data to make decisions. Decisions like, has the process improved? Or has the scrap rate come down? Has the attrition rate in a company come down? Has our on-time delivery performance improved? So these kinds of questions. And these are the kinds of questions that people want to answer. So whenever you talk about these things, people normally talk only about the average. So they say, in the last quarter, our average time to deliver. I hope everybody can hear me now. In fact, I found that I was also muted. Maybe one of you can just tell me in the chat window that you can hear me. I found I was muted actually. Everyone can hear me? Anyone say yes? Just one person. Thank you very much. Thank you, Diya Vasantakumar. Okay, very good. Okay. So the point I wanted to make here is, I don't know if people heard me when I was speaking just half a minute ago. Whenever we describe data, I want to utilize this platform to keep telling that. Always, always, always include the standard deviation. Now, if you don't have the standard deviation, there are many other measures of variation. We'll talk about those later, but you should have one measure for central tendency, which is typically the average or mean, and the other measure for variation. Typically, it's a standard deviation, though not always. When the data is highly non-normal, we use a quantity called the interquartile range in place of the standard deviation. But for practical purposes, standard deviation too. Go ahead. Next, just go ahead, Srinidhi. Now, if the population is normally distributed, what we can say is, please go ahead. Yeah, just go ahead, move ahead on all the points. So 68% of this lies between 65. When I said plus or minus one standard deviation, what it means is 68% of the population. Which population? A population which has a mean of 65 and a standard deviation of 9. You can say that 68% of it will lie between 56 to 74 kgs. 95% of it will lie between 47 and 83 kgs. And 99% of it will lie between 38 and 92 kgs. This is what you can actually conclude if you are told A, population is normal, if you're given the mean, and if you're given the standard deviation. And in spite of all this, people still are unable to utilize this concept in real life. And of course, this 1.96 number, probably some of you would have come across this number. 95% of the population actually lies exactly 1.96 standard deviations from the mean. And while this might sound like a lot of mumbo jumbo, you will find that these have tremendous commercial implications. The reason why statistics is so popular today is you can take decisions based on very simple statistics. Go ahead, Srinidhi. Yeah, and now for some bad news, after giving you all this funda about normal distribution, the truth is you never get to work with a population, right? So what do you get to work with? You get to work with a sample. Next, just go ahead. Yeah, go ahead. So we can't really use the normal. So where do we go now? And that is an answer probably some of you are aware of. Go to the next slide, please. So that is where we use something called the T distribution. So imagine you have 1,000 samples, right? Suppose you have 1,000 samples. Go ahead, just go ahead slowly, Srinidhi. Every 10, 15 seconds, you can go ahead. Suppose each sample had only 4 data points, then the plotted averages would look like this. Go ahead. If you had 15 points, you will find that the spread is slightly lesser. If you have 100 points, then the plotted averages would show even less spread. Of course, there is something called the central limit theorem, but I'm not coming to that. But what I'm trying to say is, in real life, yeah, just a minute. When we, I'm trying to answer the question. When we say we convert a distribution to normal, what does it really mean? Srinidhi, just hold the slide. I'm trying to answer this Jen's question, Prasad. Convert a population simply means, you see, for example, I don't know, there are probably 100 odd people in this session. I could probably take a list of all your weights. I could get an average weight and standard deviation. I could make a list of all your heights. I would get average height, standard deviation. I could take your IQs. I could take your blood sugar readings. I don't know, I could take several readings. Now, each of these will have a different mean and a different standard deviation. So standardization simply means you standardize in a way such that all of them can be read off from the same table. And what we do here, this is a technique called normalization, where we represent every data point as, if any ordinary data point is called xi, right? Xi means, in our case, suppose there are 100 people, so in xi, I runs from 1 to 100. Take any data point, subtract the mean and divide it by the standard deviation. This is called a normalized variable. And that is how we convert all data to, I won't say converting to a normal distribution, we are talking about normalizing data. And yes, go ahead, please. I'll answer one more question here. Thank you, and Trisha. Yeah, there's just one more point I want to say. It is highly possible that you may have 1,000 data points. It may still not be normal. The data may not be. I'm not going to cover those tests. There are actually well-defined tests for normality. Well-defined tests for normality. For example, if you were to take the salaries of all the people. Just hold the slide here, Srinidhi. I'm just going to make a point and then we'll go ahead. Let's assume that we had the table. I don't know how we got it. Maybe you got it from some of those WikiLeaks that are happening. Like recently, I heard that Domino's data has all been leaked. So let's assume that you got the salary data of a large company of, say, 10,000 people. You will find that when you plot that data, it will not look like even these figures. It will look very skewed actually. It will look very much twisted towards one end. Why? Because you will find most of the people in any organization, whether it is IBM or General Electric or even say Mukherjee and Company, Banerjee and Company, Menon and Company, even small companies or large companies, the most of the people will be earning salaries in the low range, and there will be a very few people earning salaries at a high range. So the distribution will never be normal. Okay, coming back to the, just go ahead, please. This is, I'd like to apologize. There is an ugly little formula sitting here. You can see in practice, again, this might look a bit theoretical, but I'll show you applications. Go ahead, please. You'll find an ugly little formula cropping up. Yes. So this is the basic formula. The confidence intervals is basically the X bar being the mean of the sample, the t value at that given degree of freedom multiplied by the standard deviation of sample divided by the square root of n. This is what the confidence interval looks like. But don't worry, in real life, a lot of softwares are available, and if you are interested enough, you can always sign up for any classes. But I'm going to give you an actual application of this question in the next slide. Can you go to the next slide? In real life, please understand, just go slowly. Srinidhi, maybe every 10-15 seconds you can move ahead. Okay, so you're the manager in a factory. Typically, please understand, in real life, no one is going to give you some data and say, calculate mean, median, mode, standard deviation, interquartile range, draw frequency polygon, draw a histogram, draw. No one is going to ask you all these questions. What people are going to ask you is questions like the one I'm going to ask here. So you're the manager in a factory, and you're making 500 milliliter cans of fruit juice, and the production is 40,000 cans a day. Every canning is a very high speed operation. Now what you did was you took a random sample of 10 cans, right? You just took 10 cans and you just want to check if the bottling process is okay. You must excuse me for these examples. I come from an engineering background, so you will find more of these examples. You took a random sample of 10 cans, measured them out carefully and found that the average is 502. Okay, go ahead, please. Now the question is the true average greater than 500? If somebody asked you a question like this, how would you answer? Anyone, you can just chat with me. I'll give you some 5-10 seconds and to see that they will go ahead with the slide. Is the true, mind you, the word true, you have taken a sample of 10 cans and you found the mean to be 502. By true average, I mean the true average of all the 40,000 cans that day. Do you think it will be greater than 500, less than 500, equal to 500, or what? Okay, go ahead. Slide, please go ahead. Okay, how would you measure the true average anyway? Of course, a very brilliant way would be to open all the bottles that you've made, open all of them and pour out all the liquid and measure it. But that has a big disadvantage. Then you will not have any product to sell. That's a big disadvantage. So how would you now answer this question? Is the true average greater than 500? Please go ahead, Srinidhi. And somebody gives you maths like this. So you're supposed to give 500, but you're actually giving 502. Now you're giving away 2 milliliters into 40,000. Why? Because you're making 40,000 cans a day. So you're giving away 80 liters every day. And if you're working for 330 days in a year, you are giving away 26,400 liters. Right? Your boss could say, hey, you're a useless guy. You're wasting 26,400 liters. So in real life, decision making is always of this form. Is your process line working correctly? Is your plant working the way it's supposed to? Have you really made an improvement in the working conditions in a company? Typically, HR people want to talk about attrition rates. Or for example, you're in marketing. You had a hotshot guy and you've got some higher sales. And now you want to actually satisfy yourselves. Is the higher sales happening by chance, or is it happening because you hired a new guy? All these kinds of questions, whenever you want to check whether a change has happened, you need statistics to make that decision. Please go ahead. Okay, this is the answer. Whenever somebody gives you an average, I had given you this hint a short while ago. I just told you the mean, right? You should also push back and either ask for two things. Either ask for, give me the data. Give me the data means give me those 10 numbers, because I said you took a sample of 10 cans, or you ask for the standard deviation. Next, please. Okay, so now your quality control guy comes and tells you standard deviation is 5 milliliters. I'm not going to get into the formula of the standard deviation. That's very well known in Excel. You can just type STDEV, you will get a standard deviation. And now using the formula on the previous page, let's not get into details. You can actually cross-check them. Using the formula on the previous page, you can calculate the 95%. And here, just hold the slide because this is a concept which gives a lot of trouble to people. You can calculate the 95% lower and upper confidence limits. So you can say, and I'm going to give you two interpretations of this number. I'll give you a loose interpretation and I'll give you an exact interpretation. The loose interpretation is, I can be 95% sure, please listen carefully, I can be 95% sure that a randomly selected can will contain between 498.4 and 505.6. So since 500 lies in between, I'll say that there is no significant difference between 500 and the average can content. So I'm doing good. I really don't need to make any change. So this is the loose interpretation. I'll repeat once again. Loose interpretation is, I can be 95%. And how do I get it? I use the T distribution to calculate this. And these are all very, very standard calculations. By knowing the mean is 502, by knowing the standard deviation 5, and by knowing the sample size. You just need 3 items. You need a mean, you need a standard deviation, and you need a sample size. By using these 3 numbers, you can actually say that, calculate the 95% lower and upper confidence limit. So you can say, I'm 95% sure that the can will contain fruit juice which is between 498.4 and 505.6. It's a good way of answering. Now, if you want an exact statistical interpretation, it is this. Please remember that I took a sample of 10 cans. So the exact statistical interpretation is, if you were to keep on taking samples of 10, right? So this sample of 10 gave you a mean of 502. If you take another sample of 10, you may not get 502. You may get 501.4. Another sample, you might get 499.6. You might get a variety of numbers. What the T distribution tells you is 95% of these sample means will lie between these two numbers. That's what it means. Next, please. So this is the conclusion. There's nothing wrong with the line. Average is not significantly different from 500. In other words, all this 26,400 liters down the drain, that's all buncombe. That's just a fairy tale. It's not really happening that way. Because if you're giving away more in one shift, you're giving away less in some other. So overall, you are balancing it out and there's nothing wrong with the line. Please go ahead. Okay, now simulation. This is something which is very close to my heart, and just go ahead. I'm going to show you an actual case. And this is something which I really wish I had learned when I was much younger. I'll give you my background. I started off my career by working in a consulting engineering company. Just hold the slide here, Srinidhi. Let me just give a background. So one of the tasks that people like us were assigned was costing, costing of a plant. Typically, we were asked to estimate the capital cost and work and operating cost of very large steel plants. So, typically steel plants, I'm talking of the 1990s. In those days, the order of magnitude for a mid-size, steel plant would be around 4,000 to 5,000 crores. So we would be asked questions like, so what is the chances of making a profit? Nobody really asked a probability question, but people would ask, paisa milega ki nahi? So we would do some kind of scenarios, like what would happen is during the course of building the plant, maybe the interest rates would go up. So that means your cost would go up. Now because a steel plant would take anywhere between 3 to 5 years to construct. So suppose, like I remember we were doing the feasibility for a plant producing what is called direct reduced iron, DRI. And DRI has a competing raw material called scrap, which India used to import. So now we are trying to build, we are telling a client to build the plant saying that this is a good scrap substitute. But if the price of scrap falls, then our profitability also falls. So there could be so many factors which are affecting the profitability. Now, how do you actually assign a probabilistic value to your profitability? And in fact, the example which I've given you is not so complicated. Srinidhi, just go ahead slowly. You can maybe go slightly faster. Okay, so in fact, this a friend and I, we were together working it out. So the fees you're going to charge is 45,000. Just go ahead slightly faster because you let all 10 people will attend. Okay, then 5% commission. Somebody brings you a murga or a bakra, you have to give him some money. So, okay, commission 5%. Then contingency. There could always be things which go wrong, you some extra expenses. So we'll put contingency at 2%. And then trainer fees, we have to get hold of some, either we do the training ourselves or get hold of somebody. That guy probably in the market, the 30 is the going rate. Okay, go ahead. Then you want to have hospitality, right? You hire a hotel. So it's 1,500 rupees per person per day. Now, how will you calculate the profit? Now, this is fairly simple. This is fairly simple. Just go ahead, Srinidhi, you will find the answers are given here. You don't have to bother about this. You can actually check, the revenue, total revenue is the fees and multiplied by number of people into 1 minus commission, because I'm assuming you're paying a commission on all these guys. And the expenses, this doesn't require any great mathematical abilities. The total number of participants are P, and then you add 5 more people, the organizers and some miscellaneous guys, and multiply by the hospitality rate, add the trainer rate, multiply by number of days. And then the whole thing you multiply by 1 plus contingency. This is not too difficult. Any fool can do it. And then you get a nice figure of 1.6 lakhs. So revenue minus expenses. So we'll make a profit of 1.6 lakhs. So this is how everybody does. Everybody, from very senior marketing people, or I'm talking of project feasibility, project appraisals. Whenever you're asked to appraise the profitability of a project, what people do is they get some static numbers. Okay, iska kitna hoga, uska kitna hoga, and put all these things plus, minus, multiply. This is a very simplified case, but the same thing works even for very large business scenarios. So they'll say, okay, the profit is going to be 1.6 lakhs. But now somebody asks you, how sure are you of this estimate? Then you're finished, right? You'll say, how do I know? So this is where a very simple business simulation, and I have actually run it using a very popular software called R. And I, of course, take sessions in R, and it's not very difficult. Any fool can do it. If I can do it, anyone can do it. Please go ahead, Srinidhi, for the next slide. Okay. Go slowly. You don't wait for me to tell you. Just keep going slowly. Now you're asked to estimate. Yes, go ahead. Now, okay, fine, that's fine. So fees is 45, but it could vary maybe plus or minus 10%. Actual numbers, instead of 10 people, it could be 5 to 15. Go ahead, Srinidhi. Commission could be between 5 to 10%. I mean, there is I'm putting a variation for each of this. Contingency, we are assuming 2, it could be 1 to 5%. Next, trainer fees could be 30K. I don't know, if I'm a good bargainer, I can get him less than that. But if he's a tough guy, he'll probably ask more. Hospitality could be anything, right? It could be between 1,200 to 2,000. It could be any number. Okay, go ahead. Next. Okay, now the same equation which I used, I can actually, all that I do in a simulation is I simulate the entire thing 1,000 times. That's all I'm doing. Now go ahead, please, Srinidhi, go to the next slide. Okay. Now, you don't have to, I'm not going to explain the slide. This is basically nothing but an R code. As you can see, I'm just going to tell you how it works. I'm telling R that fees is a quantity which varies like this. The mean is 45,000 and the standard deviation is 2,500. Simulate 1,000 values. So what R will do is it will simulate 1,000 random values keeping these two. Then I'd say people, it's a uniform distribution. It's not normal, it's uniform. It could be any number between 5 and 50. The difference between uniform and normal is when a distribution is normally distributed, more values are likely to come near the center than at the tails. For example, this is a conceptual point I want to spend a minute or two because simulations are very useful. So we know that the average human weight is around 68 kgs. If you have actually observed the elevators in which you have traveled in any large company, if you could just go to any elevator by any company, you find that the standard human weight is taken as 68 kgs. Now, the question which I want to ask you, you can give an answer through the chatting machine, through chat. Suppose after this session is over, you step out of your house and you find some human being coming across. What is more probable? The weight of that person is 65 kgs or the weight of that person is 100 kgs? What is more probable that you will find? Are you more likely to find a 100 kg person coming, the first person that you meet, or are you more likely to find somebody who weighs 65 kgs? It's obviously, a lot of people have said 65. So that is the property of the normal. More values are to be found closer to the mean than outside. And that is completely different from a unif. R, this second word here is R, uniform. In a uniform distribution, it could be any number. Hospitality, again, I don't know what it's going to be like. It could be any number between 1200 and 2000. And contingency, these are all uniform. Trainer, of course, I'm fairly sure that it will be more close to 30 than outside. So I'm saying, so what I'm saying is, instead of having fixed numbers, I'm assigning 1,000 different values of each and then writing these three equations. These are the same equations which I wrote, but the only thing is, R will run each of these lines, expenses, revenue, and profit. It will run it 1,000 times by taking, it will take the first value generated here, take the first value here, and run it once and calculate profit. Keep it. It will run it the second time. It will run it the third time, and it will run it 1,000 times. That's what a simulation is. And go to the next slide, please. Next slide. Yeah. So this is the actual simulated profit. So you can see here, these are called the quantiles of profit. What this means is, there is a 5% chance that you will lose money. There will be a loss of 19,354. There's a 10% chance that you'll make a profit of 40 rupees. So somewhere between 5 and 10 is the break-even point. Right? So what this also means is, if when we try to assess this, the probability of making a profit, what we can say here is, there is a 100 minus 15, there's an 85% chance that you will make a profit of more than 18,808. If you look at this number, there's a 50% chance that you'll make a profit of 1.24 lakh. So this kind of a probabilistic estimate is much, much more valuable to management rather than some dumb number like you gave, 1.6 lakhs. So today, it is very easy. In fact, there was a tool, I don't know if you people have heard of a tool called Crystal Ball. There used to be a tool called Crystal Ball. Unfortunately, it's very expensive. I just checked, it costs about 1 lakh of rupees now. It costs 1.5 lakh if you want some. What 100% is maximum. Dia, you asked a question. 100% simply means maximum. Actually, you need to report only up to 50 or even 80%. Actually, if you ask me, the first 4 numbers are important. What this means is, yeah, there's a 20% chance that you'll make a profit of 34,000 something. So you can say there is an 80% chance you'll make a profit of more than 34,000. Actually, if you ask me, in fact, even this number is good enough, as long as you don't lose money. As long as you don't lose money, it's okay. It should not happen. So the probability of losing money is very low. As you can see, there's a 5% chance that you will be in the red. But if you're willing to take that risk, you can always go ahead. So giving and mind you, this is not very difficult. You can actually, R is a language which is very easily learned, and you'll find a lot of people offering courses in R. But the trouble with most of the courses is those are more of how to use R, like how do you split tables, how do you extract data. But the usage of these tools to answer business questions, that is very important. Like it is now, today I'm 56 years old. I now wish if I had this tool 25, 30 or maybe 40, 30 years ago, I would have done a better job in able to predict the profitability of a plan. I'd have been able to tell my clients that, look, if conditions go like this, and you can have a host of assumptions. In fact, in those days, I do not know how the age profile of the participants here, but whenever large contracts are signed by companies for supply of equipment, and especially if the equipment is going to come over a long time, say over the next 3 or 4 years, all large contractors, they build in a price escalation clause, which is linked to something called CPI. The CPI is not the Communist Party of India, it is the Consumer Price Index. So you could even factor that in your simulation. You can say that if the CPI increases by 10%, the cost could go up by as high as 10%. If the price of the competitor's product goes down by 10%, then your selling price goes down, so your profitability goes down. So all these factors, if you put in a simulation, you can get a probabilistic estimate of probability of profitability, and that's very important. So next slide, please. Next slide, Srinidhi. Okay, so quality control. This is something close to my heart. I've worked for quite some time in quality control. Yes, next slide. This is just a header. Okay, so this is going to be slightly conceptual. So I'd like you people to listen carefully. So everybody, I hope, knows mean, median, and mode. I'm not going to spend much time on this. Next. Okay, that's just an advertisement which I somehow sneaked in. How do you quantify variation in a data set? I just talked about it a short while ago. Just go ahead. Yeah, just go ahead in about every 5-10 seconds. Yes. In fact, the range is something which is, I hope people know what range is. Maybe somebody can try to explain a range. Anybody knows? If suppose I give you 10 numbers, how will you calculate the range? Anyone? I'll wait for one answer before going ahead. Srinidhi, can you also see the chat window? Very good. Anushri has answered max minus min. Very good. Interquartile range is, of course, something which not many people may be familiar. Interquartile range is simply the third quartile minus first quartile. But let me not get into all those things right now. Standard deviation is fairly easy. Does everybody understand standard deviation? Standard deviation, again, is basically, I'll just take a minute off. Standard deviation is a very commonsensical approach to variation. What you do is calculate the mean of the entire data set, and then from every data point, subtract the mean. If you do that and add all the values, you will get 0. So what statisticians did was you do this particular subtraction from every data point, subtract the mean, square the differences, take the average, or rather divide by n-1 and take the square root. That's the way standard deviation is calculated, and it is the best measure of variation. So one of the things that I want you to take away from today's session, and you should be able to do that, is whenever somebody gives you data, and somebody gives you data like an average was so much, always push back and say average was so much, fine. What was the variation? Don't even ask him what is standard. What was the variation? So if it's a small data set, range is good enough. If it is a very large data set, standard deviation is good enough. If it is a very skewed data set, skewed meaning, most of the data is towards one side, typically salary data. Salary data is highly skewed. Income data, salary data, and sometimes even as in production, you do get skewed data. So where data is skewed, you always look at interquartile range. Now, in any production system, there are two types of variation. Please go ahead. Yeah. Common cause and special cause. And the reason why I'm talking about these is this is at the basis of statistical quality control, which is again not a very difficult concept to understand. Go ahead. Yes. How do you distinguish between the two? Go ahead. Okay, just stop here for a minute. And I'm going to take you through an imaginary thought experiment. Because this is a very, very important concept which many people don't pay enough attention to. Now, everybody knows what the average human body temperature is. Anybody just in the chat window, just 1 or 2 persons, what is the average human body temperature? Good Lord, everybody is very nice. 98.6 Fahrenheit. Very good. I've got up a lot of answers. No, it's not 97, it's 98.6. It is 37 degrees centigrade or 98.6. So everyone knows his answer. Now just imagine I get up in the morning, right? I mean, do you find people doing this? Get up in the morning, reach for your thermometer, take your temperature. It's highly possible it may not be 98.6. In fact, most of us, if you were to even reach for the thermometer now and measure your temperature, it may not be 98.6. It may be 99.1, It may be 98.1. It could be any number. So do you find people doing this? Take thermometer, measure the temperature in the morning. If it is 99.2, take paracetamol, wait for temperature to go down. If it has gone below 98.6, again take some drug, bring the temperature up, take a hot bath. Nobody does that, right? It's stupid. So when do you go to a doctor? You go to a doctor when you are feeling sick, right? So you're genetically coded. The coding is already done inside you, so that you know instinctively when you are sick. So when you are feeling sick, you go to the doctor, and the doctor takes all kinds of measurements and prescribes the medicine. So nobody has to tell you whether you are sick. You know when you are sick. I go to the next slide. Unfortunately, that is not so with processes. If you go to the next slide, yeah, go slowly. So yeah, now the process, just go 2 steps. Scenery, just go step by step. One, yeah. Now just stop here. Suppose a process is stable. Now this is where I want to tell you. This is just like your own health. Only you know whether your health is good. No one else knows. So similarly, suppose there is a process like we talked about, the fruit juice bottling process. It might be a process which is manufacturing ball bearings, or it might be a process manufacturing, say, mobiles. It's any ordinary production process. In fact, I am also consulting for a small company which is making snacks. Your mixture and potato chips. They are also. It's a very small company. So it all depends upon chemical processes. So if your process is stable and your decision, go ahead, please. Just press it, enter once. If you do nothing, go ahead again. Yeah, then it's a correct decision. Now just keep going ahead, Srinidhi. If your process is unstable, yeah, just keep going ahead. And if you take action, then it's a correct decision. So there are 2 incorrect decisions, and those are: process is stable and you take action, and the other one, last one, process is unstable and you don't do anything. Just stop here. So these are the classical errors in statistical test. This is a type 1 error. Type 1 error is you end up tampering with a good process. And the second one is process is deteriorating, but you just stand around doing nothing, hoping that things will change by itself. So in a real manufacturing process, what actually happens is, it's not a human system where you know instinctively something is wrong. A line could be continuously producing stuff. So you take a decision based on a sample. So typically, if it's a fruit juice bottling, you take a random sample, measure it. If you're producing, say, some kind of a component, and what is important is either the diameter or the length, you just take some measurements, and based on those measurements, you need to take a decision. So the correct decisions are this: if the process is stable and you do nothing, that's fine. If the process is unstable and you take action, that's also fine. So how do you avoid these kinds of errors, type 1 and type 2 errors? Go to the next slide. That's where I've explained the quality revolution. Now, just a minute here. I would like an answer here from the audience. When you say chess, which country do you recall first? Anyone? Russia, Saumya Moni, India. Okay, very patriotic, very good. So I've got Russia, India. One more person has said Russia, very good. So Russia 2, India 1. Maybe 3, 4 answers? Dia, so Russia 2, India 2. Oh, India is winning. Russia is winning. Okay. Okay, good. I'm happy to see engagement here. Well, actually, the answer is Russia, because they dominated the game for almost the whole of the 20th century. India, of course, India was the place where the chess was invented. It was called Chaturanga. Okay, next, please. When you say mass manufacturing, which country do you recall first? Mass manufacturing. China. Okay. China. Oh, okay. This is a no-brainer. Everybody gives China answer. Very good. Very good. Very good. Okay. Next point, Srinidhi. When you say quality, which country do you recall first? Germany. Okay. Germany 1, USA, Germany, USA, UK, USA, USA, USA. Okay, that's good. USA. Very good. I got some 5 answers. Most of it is USA. So United States is renowned for quality. Okay, good. I'm happy to hear that. Anybody else? Of course, I've got only 5 answers. Can you go ahead, Srinidhi, with the slide? Okay, just stop here. Quality is not the same thing as luxury. For example, I don't know if you've heard of this guy called Dhariwal, the guy who owns your good pan masala, that gutka, Manik Chand. Because I remember it made the headlines, it made the cover story in the Outlook magazine about 13 years back. They used to sponsor the Filmfare Awards. So this unfortunate gentleman, he gifted a Maybach car to his daughter. The car, and in those days, cost only 5 crores. So now the question is, how do you expect quality in a car which costs 5 crores? Answer is yes. Of course you expect quality. But that is not a quality, that is luxury. So what is the, can you go to the next point? The next point is that what do you think is the most important thing about quality? It must be, quality must be. No, I hope I'm not asking too many difficult questions. Durability, okay. Affordable, somebody said affordable. Somebody said affordable. Obviously, the quality has to be affordable. Because, for example, when you want to buy a suitcase, you want to buy a suitcase, okay, you'll go to any of these big shops, you might find a kind of a deal here. You may, if you're lucky, get a, oh yeah, longevity is good, okay. It's actually longevity, okay. But the point I want to make about, I have seen all the answers, all of them are very good work, guarantee, warranty, I can see all these answers. The most thing about quality is that it must be affordable. For example, you can also buy Louis Vuitton suitcases. They might cost more than ₹1,00,000. Not everybody has ₹1,00,000 to buy a Louis Vuitton suitcase. So the country which made quality affordable, now can you think of it? Which was the country which made quality affordable? Anybody would like to guess? Okay, I've got 2 answers. India, Sanvi, I really appreciate your patriotism. Okay. Dia says Japan. Anybody? I can see 2 Japans now. Anybody else for Japan, Korea? In fact, I remember I asked this question in a class and somebody said Afghanistan also. I was really shocked. I don't know on what basis they said that. Well, the answer is Japan. Just go ahead. Please go ahead. Srinidhi. It brought about a revolution in quality, and I'm just going to spend a minute or so talking about this. After World War II, it was the Americans who had the monopoly because they were the winners in the war. And you had those 3 big motor companies, motor car companies, Ford, General Motors, and Chrysler. They were the companies which dictated quality. And did, in fact, as an aside, I don't even know if you know that, all European countries and first world countries, by first world countries, I mean the whole of Western Europe and the whole of, I would say, Singapore, Japan, all these advanced countries, they have got excellent public transportation. The only advanced country which has a very bad public transportation is the United States. Why? Because the automakers actually lobbied actively to ensure that public transportation is not good, because if public transportation is good, nobody will buy their cars. By the way, I'm not a conspiracy theorist. These are all available. I was trying to make a point here. Now, these 3 automakers, the Ford, General Motors, and Chrysler, they were the people who dictated quality, dictated prices, dictated everything. And sometime in the 70s, Toyota slowly started exporting cars to the United States. And at that time, you had more women entering the workforce. So whenever families, the middle class families, whenever they were looking at a second car, they decided to buy Japanese cars. Why? Because Japanese cars were very cute. It had a totally different styling. They were very inexpensive and very light on fuel. The American cars, the Buicks and the all those Chevrolets and all those cars were humongous fuel guzzlers. So they had the cars were very cute looking. They were very inexpensive. First cost was inexpensive. Very low maintenance. That is, once you buy a car, it doesn't stop. You don't really have breakdowns. You don't have to worry about spare parts. And it was very low cost. So slowly what happened was this revolution actually started to beat the Japanese. and beat the Americans. So slowly the American public, from making the car as a second car, they slowly started buying their first cars as Japanese. And before you could realize it, by 2004 or 2005, Toyota was almost set to overtake General Motors as the largest motor car company in the United States. So now, when the revolution started happening, and that's one great thing about the Americans, they have a very simple philosophy. If you can't beat them, join them. Just go ahead, Srinidhi, to the slides. You might find that this is a bit disconcerting. I'm talking about statistical quality control chart, but I'm going to link it to Japan. In fact, they were invented by Walter Schuhart. Please go ahead slowly, every 10 seconds you can go. These are based on the normal distribution which was developed in the 1820s. Yes. So this is what I was trying to say. When the Japanese started to whip the Americans in the late 70s by producing cars, as I said, just go ahead. Please go ahead. More reliable. Yes. More fuel efficient, less expensive. Yes, go ahead. The Americans asked him the secret of the success, and they gave one man's name, and that was Deming. And what did Deming do? Go ahead, please. He taught statistical methods, specifically control charts. And the Japanese said, they actually went on record saying that whatever improvement, the so-called excellence and quality that we have today, we actually learned it from an American, and they actually put these control charts in practice. They actually started applying these control charts, and the control chart actually, in Hindi there's a phrase, "Doodh ka doodh or pani ka pani." What the control chart actually tells you in a nutshell. I'm not going to get into the construction of control charts, but what does it do? It does the same thing which you do automatically about your body temperature. Like, you know when you are feeling sick. Similarly, what the control chart does is, if you give a control chart a series of measurements, it will actually tell you when the variation is common cause, that is when the variation is ordinary and you don't have to worry about it, and when the variation is actually because of some special cause where you need to take action. Go to the next slide, please. Next slide, yeah. So this will go fairly quickly here. This is a funnel experiment. I thought, I was wondering whether I should talk about it or not, but it's important that you understand this. This is a very classic experiment devised by Deming to explain the concept of variation. So this is a simple thing, you take marbles from here and put it on the funnel on top, and the marble falls below. And all that you do is record how far the marble falls from the center, the target. Just record that. So there were two strategies. Please go ahead, Srinidhi. Yeah, go ahead. Yeah, once more. Stop. Okay. So there are two strategies. So first you run 100 marbles. Like, take marble one, put it inside, watch where it falls, and just record the distance. Don't do anything. Just put one after the other and just keep recording where the marble falls. Where if the marble could be falling either to the left or to the right of the center. The second strategy is move the funnel an equal and opposite direction in an attempt to compensate. So what basically the second strategy does is, if the marble falls to the left of the center, then try to pull away the funnel to the right. If it falls to the right, then push it more to the left. You keep tampering with the system. So those are the two strategies. Next slide, please. Yeah, go ahead. And this is a classic, this is a very, very classic graph, which is Deming's experiment results. You can see here, when you did not tamper without adjustment, is the dark blue. The total variation meaning from bottom up, the total variation is much less than what you get with constant adjustment. So this was actually a big eye opener for people. Next slide, please. Yeah, go ahead. The second strategy actually showed a variation of 2 times. So what was actually happening was, go ahead, just go ahead. What we saw in this experiment, what we saw just now was random variation. Now, what was happening in the actual factories in the United States was, there was no statistical control. So what was happening was, people would frequently be making type 1 and type 2 errors. So somebody would say, hey, I don't think the line is working right. Stop the line. When actually there would be nothing wrong with the line. The type 2 error would be, somebody comes to the boss and says, so how's it going? And they just look at each other and say, yeah, I think it's doing okay. How do you say okay? By just looking at the data. But the point here is, on what basis do you say whether the variation that you are seeing is right or wrong? They did not use all these charts, and the charts which were developed by an American, in fact, control charts were developed by a man called Schuhart, who was an American. It was taught by another American called Deming to the Japanese. All that the Japanese did was they just applied it on the shop floor. So go ahead, please. So by using the control charts, they were actually able to prevent type 1 errors. Type 1 errors is very, very serious for the producer, because what you're doing here is you are rejecting good product. So if you're rejecting good product, what happens? Your cost of production goes up and your sales goes down. So by actually implementing statistical methods in the workplace, the Japanese were really able to whip the Americans. In fact, when Japan started manufacture in the mid 1950s, the Japanese had a reputation for terrible quality. In just 20-25 years, they were world class. So that's what tells you that the statistical methods, the normal distribution, which was invented sometime in the 1800s, the statistical quality control charts, which were invented in the late 1920s, they were all applied. In fact, they are relevant even today. I myself ran a SQC program in one of my companies where I worked, and we were significantly able to reduce type 1 errors. Go ahead, please. Next. Yeah. So of course, I'm not going to get into the construction of that. That's a separate subject. But what you can do here is, if you have a proper control chart, a control chart will automatically generate these limits. So the moment a data point goes above the control limit, then you know that your process is going out of control. If you don't have a control chart, you have no real means of estimating whether the variation is significantly changed in the process or whether the variation is random variation. So Deming said, understanding variation is the key to eliminating quality defects. Go ahead, next please. Okay, hypothesis testing is again, now let me just see how much time I have left. Okay, I have enough time left. Everybody knows the meaning of the word hypothesis, anyone? Hypothesis, just try to chat on the window. Just give me a very, very brief understanding of what hypothesis is. Conjecture, very nice answer, Trisha, very good answer. Conjecture is a very nice English word. Of course, I would settle for a word like theory, and assumption. So you go ahead, next slide. So this is again another paradigm whose relevance remains unchallenged even today. And these were the people at the forefront. Of course, between these three people, they had a lot of disputes, and even today, there are two different paradigms of hypothesis testing, but we will go by the most common one. That is the one which uses a p-value. So Gossett is the same guy as student. He used to call himself student for various reasons. His company had said that don't publish your name, don't publish the company's name. So all the statistical work that he did, when he was an employee at the company called Guinness. I don't know how many of you people have had Guinness. Guinness is the national beer of Ireland. If you ask me, it tastes absolutely terrible, but it's a sort of badge of honor for the Irish. So Pearson, of course, the Pearson's correlation coefficient, and Ronald Fisher, of course, I would, more than a statistician, and I would actually call him a polymath, a man who was accomplished in several fields. So this hypothesis testing, I'm just going to look at two very simple examples. Next slide, please. Yeah, you can just go ahead. Please go ahead. Yeah. So typically a null hypothesis, actually, this again causes a lot of problems to people. But what I tell them is, null hypothesis typically is a pessimistic stance. We say there is no change unless you bring in sufficiently strong evidence. And typically in the workplace, we generally are trying to prove that there is a change. For example, you have hired, as I said, you have hired a new marketing manager in the hope that marketing campaigns will be better, hence sales will be better. So you have probably sales data for last year, and end of this year you've got a new guy, and you want to now show, rather if you are the CEO who has appointed this guy at a fancy salary, you want to show that this guy has made a difference. But the statistician, what he'll ask you is, he'll ask you data before you appointed this guy, maybe 12 months, 24 months. He will ask you data after you appointed. And then the null hypothesis here, as I said, it's pessimistic. Null hypothesis here would be of the form, there is no change in the sales before and after appointing this salesman, marketing manager. And then, of course, you do a particular test. In this particular case, it's a 2-sample t-test. And based on the p-value, if the p-value is very low, you reject the null hypothesis and conclude that there is a change. That's how it works. Please go ahead. I'm just covering null hypothesis in a very, very superficial manner here, because this actually requires an entire session all by itself. But the point here is, any kind of assertion, if you want to make an assertion, must always be accompanied with data. For example, I'll give you a case where I was involved. This is again a very it's from the chemical industry, but it's very interesting. There was a pilot plant. A pilot plant is a very small kind of plant, and it was sitting in the Netherlands. It was dismantled and brought to India and set up. And I was part of the team which was involved in this. And the question now was, okay, how do you prove that you people in India have assimilated the technology? As I said, in real life, nobody will tell you, calculate this, calculate that, do this, do that. No one is going to ask you these questions. People are going to ask you realistic questions. Realistic question is this, that look, we had a pilot plant in Europe. They were operating it for so many years. Now we've dismantled the plant and brought it to India. You Indians have set it up. How do you prove to us that you have understood the technology? That's all. That's a question. Now we have to translate it into statistical terms. So what we did was, after we set it up, we said, okay, fine. So let's look at data. So we asked the Europeans who are running the plant, do you have data for your plant under so and so conditions? There are typically some conditions called baselining conditions. So you run the first reactor at this temperature, run the second reactor at this temperature, put this pressure, whatever, some conditions, and you see what the output is. The output typically is a polymer. And how do you measure the polymer? We measure something called a molecular weight. So I have output data corresponding to certain sets of inputs. Now what we did was, we had the same inputs. And we got some data, and our job was to show statistically that there is no difference between our data and theirs. So the entire practical question we converted to a statistical question. You can you go to the next slide? I'm going to give examples of hypothesis testing here. Yeah. Next slide. Good. Okay, so we are coming to this Shaguni example. You remember the Shaguni example? Just go ahead. Yeah, just go ahead slightly fast. Okay, I'm getting a message saying my internet connection is unstable, but okay, how many sixes do you expect? Just stop here, Srinathi. How many sixes do you expect in 600 throws of a die? Actually, it's 600 by 6, which is 100. Suppose you get 102. That was the question I asked last time. Go ahead, just go ahead, please. How many heads do you expect in 100 throws? I've asked this question again. Please go ahead. Yeah, just keep going ahead. Now stop here. The null hypothesis is there is no difference between the expected behavior and observed behavior. This is a null hypothesis. But it's not enough if you just state the null hypothesis. You have to do the correct test. The correct test here is a test which is highly misunderstood and it causes a lot of fear to people. It's called the chi-squared test. So if you apply the chi-squared test, just go down below. The chi-squared test actually tests for the difference in behavior, what is expected and what is observed. So if you just go ahead, just keep advancing the slide. Yeah. For the coin, it is 59 heads. And for the die, it is 117 or 83 sixes. What this means is, if you get 50, 51, 52, 53, up to 59 heads, you really can't say whether there's a difference. More than 59 heads, or in fact 100 minus 59 or 41, less than 41 heads or more than 59 heads, if you get, then you can conclude with 95% confidence that there is something wrong with the coin. And similarly for the die, this number has been calculated. In fact, if you're interested, I can show you the calculation. You will take me at face value here. And this test was developed by Carl Pearson. The chi-square test as we use it today was developed by Carl Pearson way back in 1900, and today we are in 2021. Even that's why I put the title of this talk as the relevance of statistical methods today. Now you might think, all this thing about cards and dice, these are all academic questions. You go to the next slide, which is a very, very interesting example. Okay. I hope everybody can see this. I'll spend about 4 or 5 minutes. This is an actual case study. I hope everybody can see this. So basically a very large industrial house in the National Capital Region, they had called me for some training work, and before the training started, I was asked to go and sit in some reviews. So there was a marketing review going on, and I had a terrible reputation as a statistician, so I was just asked to go and sit and listen to what people, and I had no clue what these guys were doing. And this was a very, very interesting example. So this company, I'm not going to name its main product because then you will be able to understand the name of the company, but this company was trying to get into the white goods business, basically the consumer goods. They were trying to get into mixies. They were wanting to manufacture mixie grinders. Now they don't have the competency, so they identified 7 vendors. You can see model 1, model 2, model 3. So they got 7 working models from 7 reasonably good companies which were making these for other companies. And what they did was they went to 10 towns, 10 towns, T1, T2, T3 up to T10. I don't know if you can see the number here. Can all of you see the number here on the screen? I can't see the number. The first number should be 293. Can everybody see that? Just one of you say yes, it's okay. Good, thank you very much. So look at this campaign now. They have taken model 1, and what they've done is, and look at the amount of money they've spent. I would imagine they would have spent easily a couple of crores, because you have to get these 7 models working, right? So you have to pay the vendor for getting these models. Then you have to undertake a trip, about 5 or 6 marketing executives, 1 manager, 1 VP. They will go to all these 10 towns. Then they will hire some 5-star hotels, and then they called 200 housewives in each of these towns. That's why you can see the total is 200. 200 housewives were called, and for high tea, snacks, and all that. Obviously, they will not come if you give them nothing. And these 7 models were shown, and they were asked to pick their favorite model. That's all. So they collected data from the field. So this means that in town 1, 33 people liked model 1. This number means in town 5, 40 people liked model 4. So they built up a huge table here. And then that's where, I stopped the discussion and I asked them, so which model are you going to select? And I'm going to ask you people that question too. So which model is the best? You can just chat and tell me. Second, okay. I'm not saying no to Aparna. Aparna has been kind enough to answer at the beginning. Second model. Okay, very good. Anyone here? Of course, Aparna, your other people listening are very careful because they are thinking, this fellow wouldn't be asking this question if it is so simple. Anybody else wants to say something? Okay, Anushri says model 2. And in fact, I don't blame Anushri or anyone. Everybody will say model 2. Why? Because that is the one which got the maximum number of votes. So at that point of time, I stopped the discussion and I asked these people like you, 5. Somebody says 5, 305 is this one. Okay, that's very close to that. Okay, why do you say 5? Okay, somebody says model 6. Okay, so it's a guesswork now. People are coming up with random numbers. Good. So now I just asked these people, variation will matter. That's a very good answer. Prerana matter M5. Okay. Variation will matter. You are more or less onto the truth. Okay, I'm going to rephrase the question now. Instead of asking you which model, I asked this question to the marketing guy who was presenting, and he was quite offended. I mean, he looked at me in a strange way. He said, I asked him, so which model will you select? He said, so obviously M2, like everybody said M2. So the question I asked is, Let's assume that you had taken these 7 models and gone to the same towns, but instead of these 200 housewives you called in each of these, you called another set of 200 housewives. Everybody clear? Instead of calling the first set, you call a completely different set of 200 housewives in each of these towns. Will these numbers on the right, will they be same or different? You can chat and tell me. Will they be same or will they be different? Obviously, it will be different. Thank you, Trisha. Obviously, those numbers will be different. So now the question is, how do I know that this 307, I can't see the number here. This is the highest number, 317 or whatever, I think. How do I know whether this number has happened by chance or not? So therefore, again, here I do what is called the chi-square test. And the chi-square test is very, very simple in its construction. So there are a total of 2000 numbers, right? Well, there are 10 towns, 200 people each. So 2000. Now, the null hypothesis here would be there is no difference between the models. The null hypothesis is always of that form. Like suppose you're saying that I've improved the reaction yield. So I've got data before and I've got data after. The null hypothesis would be there is no change in the reaction yield before and after your improvement claims. Somebody has increased sales. Null hypothesis, there is no improvement in sales before and after your process. Somebody claims I have reduced time to repair. No, so you have got data before process improvements, data after process improvements, and null hypothesis will be there is no change in repair times before and after. And then you have to apply the relevant tests. In this case, the null hypothesis here is there is no difference between the models. If that was so, then the expected value, as I said, the chi-square tests differences between expected value and observed value. The expected value for each of these cells here would be 2000 by 7. If there is no difference between the models, all these numbers should be the same, which should be 2000 by 7. And you define a characteristic called chi-squared, which is nothing but observed value minus expected value, square of that divided by expected value. Don't ask me why. That's the way old man Pearson formulated it. And then you calculate the chi-squared and compare it with the standard value and then accept or reject the null hypothesis. So when we actually did the chi-square test, we found that the evidence is not strong enough to reject the null hypothesis. In other words, all the models are more or less the same, and whatever variation that you're seeing here is happening only by chance. It is not because any model is inherently superior. And in fact, there's some good news also. After this, in fact, the guy who was big boss was actually my old colleague. He thanked me profusely at the end of the session, saying that even I missed it. And he was a guy whom I used to admire a lot. He was a fantastic guy. But sometimes what happens is you do make mistakes, when you're doing your work on a routine basis and when you don't have time to refresh yourself, which is why I'm very happy with all of you for having taken the time to come here. Next, can you just go ahead, Srinidhi, with the slides? Yeah. So in other words, null hypothesis, we do not have enough evidence. We got a p-value to be much higher than 0.05. I don't remember the exact value. It's there in one of my Excel sheets, but it's not good enough. The p-value should have been much lower than 0.05 for us to reject. Next slide, please. And the second example, which is coming up, this is again, very, very important in today's case. Lots of companies are coming up with lots of drugs for COVID association. Basically, this was depression. So what they did was, we have Siddha, so many systems of alternative medicine. Even in the United Kingdom, they also have, the traditional home remedies. But there is a plant called St. John's wort, which is supposed to have certain properties which will cure depression. So a clinical trial was actually done. So you recruit 200 people and 100 of them you give a placebo. A placebo meaning, just there's nothing in the drug, some harmless sugar or whatever. And another 100 you actually give the drug. But This is a blind trial and no one knows who's getting what. Like the person who's getting the drug, who's getting the tablet, he does not know whether he's actually getting a real drug or whether he's getting a placebo. So that's a very important, because there are things called psychosomatic effects which are very important in these things. So in order to ensure that uniformity of feelings, nobody knows who gets what, but only the person conducting the trial knows. Go ahead, please. Next. Now, 19 people from the first group. Just stop here. So the first group is the placebo group, that they've not got the drug. 19 people out of 100 said that they felt better. So that is the psychosomatic effect. And 27 people from the second group reported similar benefits. Now the question is, the second group is the group which got the drug. Now the question is the drug really beneficial or not? You can answer yes or no in a chat window. I'll give you one line of argument. Placebo means no drug. Placebo basically means no active ingredient. So those number of people is 19. Number of people who got the drug and received improvement is 27. 27 minus 19 is 8. It's nearly 50% more. One person has said drug is not beneficial. Why? After all, 27 is higher than 19, right? It's about 40% more. 27 is 40% more than 19. So why did you say no? One person said no. Okay. Same person, Kiranjit, has said out of 100 only 27. Okay. Right. Anybody else wants to say anything? My point is, what is wrong with my, I'm not claiming to cure everyone. I'm only saying that the drug is better than the placebo. Therefore, this is where the utility of statistical methods lie. For example, Kiranjit has given one answer and probably the other people don't want to show their hand, but you will find if you ask 50 people, you will find half of them says yes, half of them says no. So on what basis? Today, in fact, whenever you want to write any paper, I'm not talking of academic paper, I'm talking of even you want to present some findings to your management, you want to present a paper either in a industry forum, or you're writing an academic paper. Whenever you want to present your work, if you don't have a solid statistical basis, no one will take you seriously. And please go ahead. I've given the statistical explanation here. The null hypothesis here again, by now you're probably familiar with the way it's stated. The null hypothesis, please go ahead, just go ahead. There is no difference between the placebo and the drug, and the relevant test is, of course, those who have not undergone a statistics class will not know the test. For each of these various categories, the tests are different. The null hypothesis has the same format, but the tests are different. There's the two sample t-test of the proportion. P-value is very high, 17.17. Since it's much higher, 0.05, you will not take the risk and you will say that there is no significant difference between the placebo and the drug. So this, by the way, this paper is not some ordinary paper. It is published in the Journal of the American Medical Association. This has been copied from there. Next, please. Okay, regression. Regression is something I think we are more or less, okay, I just have another 20 minutes. Regression is, of course, the most widely used tool, and I'm just going to talk about one or two things. So please go ahead. Simple, in just go faster. I want to complete the slide quickly. Yeah, so in regression, what we do here is, the term was coined by Francis Galton when he was trying to investigate the relationship between the heights of fathers and the heights of sons. But today, the whole of regression is based on the principle of least squares. And it's a standard tool and everybody uses it. It's, as I said, it's the workhorse of scientists and engineers. Please go ahead. You can go ahead slightly faster now, Srinath. Yeah, it's not only among scientists and engineers, a lot of sociologists, psychologists, all kinds of people use regression. And it works on the principle of least squares, which was developed again by our friend Carl Friedrich Gauss. and the French mathematician Adrien Marie Legendre. So now this, I'm not going to get into the computing part of this, but basically what does regression do? It tries to give you a mathematical relationship between two variables y and x. So much so that if you know x, you can predict y. Go to the next slide, please. Next slide. Yeah, just go ahead. In fact, these are all the kinds of examples, between mileage and engine displacement. Yeah, I know it's coming slowly. Steam usage and ambient temperature. Why do we use this? Because this is basically for plant control. In fact, when the ambient temperature is very cold, the steam usage will be less. So if you can develop a mathematical relationship between the ambient temperature and the steam usage, you will be able to predict what your monthly steam usage will be, and hence you can optimize your boiler operations. I mean, so there are actual industrial uses of this. Noise exposure and hypertension. This again is a medical study. People wanted to check, is there any relationship between the military equipment out there? The noise will be very high. So is there a relationship between the noise exposure and the hypertension of the patient, of the worker? Then of course, this is very common: advertising expenditure and sales, thrust and exhaust temperature. Thrust is something which you can't measure easily, but you can always measure the exhaust temperature. So if I can measure the exhaust temperature, can I predict the thrust? So this kind of a mathematical, and this is fairly straightforward. It's not very difficult, and I've explained here. Can you just go ahead, Srinidhi? I've given a very brief account of how it is done. So first you obtain the data. Data means basically X and Y, set of X and Y. Fit the linear model using any software. You can use Minitab, you can use Excel. In fact, Excel also does a pretty good job. You can use R, you can use JMP, SAS, and anything in the world. Of course, checking the model adequacy, that's where a little bit of statistical maturity is required. And the last part is slightly tricky. If your linear model doesn't work, SL, the L stands for linear. If your system is non-linear, then the model may not work, in which case you'll have to look at different kinds of non-linear models, etc. But that's not the point. The point is, the regression as a tool is used to develop relationships, mathematical relationships between one or more y versus one or more x's. But the thrust of the point here is, I'm talking of a different kind of regression. Can you go to the next slide? That's something called logistic regression, which most people have probably heard of, but not, in fact, how many of us have heard of the Space Shuttle Challenger? Just say yes or no. No, okay. Everybody's heard of Columbia? Columbia? Kalpana Chawla? No. No one has heard of Kalpana Chawla. You're making me very sad. This is supposed to be women in big data. No women have heard of Kalpana Chawla. You're breaking my heart. Okay, so Kalpana Chawla died in the Columbia space shuttle, but that was I think in the early 2000s. But this Challenger was a big news. It happened in 1986, I remember, and I was studying, I think, in my third year chemical engineering. Just go ahead. It blew up 73 seconds after takeoff. Just 73 seconds after takeoff, it blew up. Obviously, all the 7 crew members were killed. It was a big tragedy, and not only that, then the whole of America went into mourning. The whole of the United States went into mourning, and it was a big thing. In fact, so then people obviously, I think it was the Rogers Commission. I don't remember the name exactly. Commission was appointed by President Reagan to find out why it happened, and you won't guess what the root cause was. Just go to the next. Next. It was caused by the failure of an O-ring seal. Whenever two metal members are joined together, you would have found the seals in many applications. Whenever you're joining two metal parts, in order to make sure that no air gets in or goes out, you put a seal inside, an O-ring seal. So you won't believe it, an O-ring seal actually used in the joint of the solid rocket booster, that failed. And as a result of that, the entire uh, rocket actually failed. And the O-ring failed because it was not designed to withstand low temperatures. But the tragedy is not this. The tragedy comes ahead. Just go ahead and you'll understand what it is. failure data of the seals with respect to temperature was already available before the launch. That's the tragedy. And so now this kind of regression, in the previous regression that we talked about, we were trying to predict the value of y given the value of x. If I know the ambient temperature, how much will the steam consumption be? If I know the exhaust temperature, how much will the thrust be? If I know the noise level, how much will the hypertension be? So it's a question of numbers. But a logistic regression is more tricky. A logistic regression is basically of a yes-no type. If I know a certain condition, will this equipment fail or not? It's of a yes no type. And that's, so will the o-ring fail or not? So basically a logistic regression, if you give failure data in a logistic regression, it will give you the probability of failure. Please go ahead. Go ahead. Just advance the slide. So this is the data. As you can see here at 53 degrees, this, by the way, it's in Fahrenheit. 1 means failure has occurred and 0 means no failure has occurred. So this data was available. Temperature, when the temperature is 53, it has failed. 63. So you can very clearly see that even though there have been some cases of failure, most of the failures are occurring at the low temperature. And it does not require a great logistic regression to tell at 53 degrees centigrade. In fact, with this data, it is possible to develop an equation. I'm not going to get into how to develop it. That will be the subject of my regression classes. But given data like this, given this is pass-fail data, at this temperature, has it failed or not? This is the question asked. And Srinidhi, if you just advance the slide. Yeah. You can see the equation is at the bottom. I'm not getting into the details, but this is the y is actually the probability of failure. And unfortunately, this equation looks a bit sticky. This uses what is called the exponential function, and this exponential function is basically the very nature of the logistic regression equation. You can actually use this equation to predict. So if you put the value of the temperature here, temperature equal to, in fact, on the day of the launch, on 20th of January 1986, the actual temperature, ambient temperature outside was 31 degrees Fahrenheit. 31 degrees Fahrenheit. So if you put that value 31 here in this equation, the y comes to nearly 1. So it was dead sure that you would fail. And in fact, I've taken this example from the classic text by Douglas Montgomery and George Runger on statistics for engineers and scientists. Montgomery says in his book that the Challenger disaster is a classic example, or it's a reason as to why engineers and scientists must have a thorough grounding in statistical methods. Because this data was available much before the launch. Nobody had taken the trouble to analyze it. Next slide, please. Okay, so I think we are doing reasonably good for time. Experimental design is something which is very close to my heart, but I'm not going to spend too much of time on this. Go to the next slide, please. DOE is a subject which causes a lot of heartburn and other things to people who study this. In fact, I too had a lot of problems understanding it. But for scientists and engineers, this is an absolutely invaluable tool. And what is DOE? It basically consists of purposeful changes of inputs to a process in order to observe the changes. This may not make much sense to you, but what I'm saying is this. Let's suppose that you are designing an engine. Right? Today, you've got very stringent pollution norms. Somebody says, I don't care what you do, but I want to ensure that the nitrogen oxide emission from this engine is below this number. Now, there could be many things that affect it. Maybe it could be the design of the engine. Maybe it could be the type of fuel used. Maybe it is the type of firing cycle that you use. Even with different engines, you would have different kinds of firing cycles. There could be probably 6 or 7 variables which affect the nitrogen oxide emission. The question now is, how would you know which is the most important factor? Or for example, in in you're trying to optimize the chemical reaction, which factors are most important? Or in fact, the design of experiments have been also done in, you won't believe it, it has also been done in non-technical areas. For example, advertising campaigns. Advertising campaign, you can look up, I'll try to give you a link to that. For example, somebody was trying to check, uh, do we need 4-color printing or 2-color printing? Do we need paper? I mean, do we need postcard size or bigger size? This is the days before online adverts, and send it by mail. So very large companies have actually done experimental design in non-scientific areas. In fact, Anheuser-Busch, in fact, the company which makes the Budweiser beer, they also had done a lot of experimental design in trying to optimize the marketing strategies. What kind of serving size, what kind of serving size, what kind of packaging, what kind of areas, what kind of outlets. Are you able to understand? So what particular combination of these variables will result in maximum sales? The approach to solving that problem is exactly the same as engine design. What combination of factors will be best in order to have minimum nitrogen oxide emission? So that's what DOI does, and it is not a substitute for scientific knowledge, but it's a very good supplement to scientific knowledge. Next slide, please. As I said, it's the effective method. Yeah, you can just go ahead to identify key input factors. And of course, the most important point is here. This may not be of much interest to you, but it's more important for engineers and scientists. So it will actually help us to understand interaction effects. And of course, you can build mathematical models. This part of the DOE is somewhat slightly technical, so I'm not going to spend much time on explaining this. But for those of you who are interested, we also offer experimental design programs, and there we will discuss these things in great detail. Next slide, please. Okay, I've just given you a history. Many people seem to think that all these statistical tests that we do today, that's a tests and ANOVA and all these kind of tests, they've all started from engineering. Actually, nothing could be further from the truth. All these tests were all invented by the great Ronald Fisher at the agricultural station in Rothamsted in the United Kingdom. Just please move ahead the slides. Of course, the analysis of variance transfer ANOVA and the factorial designs and all these basically concepts. Please go ahead. So there were 4 eras of experimental design. Today, experimental design is a very, very important tool. In fact, that's how people like me have managed to make a living. Many large companies, in fact, right now, just stop here for a second, Srinidhi. I'm just going to take a half a minute to explain this. Experimental design is not, as I said, it's not limited only to chemical companies. As I said, even a beer manufacturer like Anheuser-Busch actually spent a lot of money in running experimental designs. Advertising agencies have also spent a lot of, basically, it's also called A/B testing, where you want to check the effects of combining several factors on some particular response. So this is basically history of DOA. It's fairly important that we remember this. The second era, of course, was started by Box and Wilson. This may not be very important for you, but today many companies, whether they're medium-sized companies or large companies, whenever they are trying to improve their products and processes, the only way to go about it is by using DOEs. Next, so DOE is a very important tool in the statistical tool set. Next, please. Then, of course, Taguchi. Taguchi's works, I do not know if you are familiar with an Indian mathematician called Kalayampudi Radhakrishna Rao, C.R. Rao, who now lives in the US. He's a fellow of the Royal Society and a great man. A lot of Taguchi, but Taguchi is the more famous man. The Taguchi designs today are known to almost all scientists and engineers. The work of Taguchi was actually based on the mathematics developed by C.R. Rao. And as I said, the word robust, making processes insensitive to environmental factors. So how do you, for example, how do you design an air conditioner or a refrigerator which doesn't mind very high or very low temperatures? For example, if you design an air conditioner It must work in Chennai where the outside temperature may be 40 or so. It must also work in Ooty where the outside temperature during summer may be only what 20 or so. It must also work in Jaipur where the temperature will go as high as 50 degrees. It must also work in a very moist environment. It must also work in a dry environment. So those are all the environmental factors, and making processes insensitive to environmental factors is a very, very important concept in statistical process design. So again, the work of Genichi Taguchi actually helped to utilize statistical methods to develop these kinds of products. And the Americans, of course, God bless them, the greatest thing about them is no matter where they get it, if they find something good, they copy it. Go ahead, next please. Okay, I can see from my watch that I have 2 minutes. I'll probably take another 3 or 4 minutes more and we should be done. Yeah, you can skip the slide. Okay, you can. This is, of course, Fisher is a person whom people like me worship a lot. And there's a very simple quote here. Next slide, please. This is just an, this is a very famous quote. Huh? Many of the most useful designs are simple. Fisher also had a very good sense of humor, and it was a very dry, typical British humor. You would have to read his books 2 or 3 times to actually understand the humor in his text, which were actually very dry. Next slide. This is the application of DOE. You can see almost everywhere: chemical, metallurgical, automotive, electronics manufacturing. Pharma actually uses a lot of DOE, and I've been very fortunate to work with pharma companies also in helping to set up their DOEs and analyze them. Food and beverages also. Yeah. Next, please. Okay, so we've come more or less to this is the only concession I've made to modern, because most of what we have done so far is the conventional statistics, the tree-based methods. Are people familiar with something called CART, classification and regression trees? You just need to say yes or no. No. Okay. Anybody else? Anyone? Okay. So I would assume not too many people are familiar. Okay, so there's one more person who says no. Okay, please move ahead. I promise you, and then we have come to the end. Thank you very much. 3 people have said no. So you see, the thing is, as we start using more and more computing power, the thinking becomes more and more simple. In fact, this regression that I talked about just 20 minutes ago was based on a principle of least squares. I'm not going to explain least squares. It's a slightly mathematical concept, but that kind of regression tool works very well. It works very well. And of course, the logit function, which I showed for the failure of the O-rings, where you use the exponential function, those are called logit functions. Now, this actually works. But when you have very non-linear data, so when you have very non-linear data where the response is not linear, we use what are called tree-based methods. And this tree, again, it may sound very complicated. What this does is, as you can see here, if I wanted to give an example, but then there wouldn't be much time, but I want you to just think with me. Let's suppose that you are trying to predict something. You're trying to predict, for example, the salary of a person. It's very important that you should be able to predict given certain variables. So what would be some of the most important variables? Typically, how you do it, if you are not using a tree-based method, because I've used this actually in real life, I was also working in HR. Typically, what we do is we try to get some data. That is called the training data set. Training data set, what we get is, we actually try to get a huge matrix of data where we have, say, a person's education, age. So education is basically a discrete variable. You can have either high school, graduate, postgraduate, professional. So you could have 4 categories. Age is a continuous number. Then you could also have the kind of company that is working in. Is he working in a Fortune 500 company, or is he working in the next level of company? Okay, then you could have the kind of environment that he stays. So there could be several variables which could actually affect that person's bargaining power. So based on that, you can actually develop an equation whereby if you put in all the values, you'll be able to come up with a value for the salary. That is the way normal regression works. How a binary classification works, how a tree-based method works is, you try to put in certain rules into it. So you could put in a rule saying that, for all guys who are between 20 and 25, assume that this is going to be the salary based on the data. So what this basically means is it's not very rigorous. It's not very rigorous, but when we are looking at huge amounts of data, the tree methods actually work better than the classical least squares method. I do not know if I've made myself very clear, because in order to explain tree-based methods, I need to open R and I need to have actual data whereby you can actually see it. So all that I want you to take away, this is the second last slide. There's one more slide based on the same thing. So when will you use trees and when will you use classical methods? You will use classical methods when the relationship is more or less linear and when the number of data points is not very high. But when you have a humongous amount of data and where you suspect that the relationship is not very simple, where it's complex, then you will use tree-based methods. Next slide. Hopefully that is the last slide. Okay, this part I don't even want to talk about it. Okay, please go to the next slide. Yeah, this is something. Yeah. So these are the pros and cons. This is what I want people to leave with, that the pros of trees, the plus points are, easy to explain and it mirrors human decision making. For example, um, a policeman, when he's trying to catch people while they're on the streets, for violating the protocol, if the guy is in a car and well dressed, he has a certain rule in his mind. If the guy is well dressed and he's in a large car, maybe he's a big shot, so he may not take action against him. So in other words, there are some rules built into him. So similarly, the trees actually use certain kinds of rule making which you can actually incorporate into the program. And of course, you can actually display it easily, very graphically. On the other hand, this is the minus point. The predictive accuracy is not very good. It's not very robust. But today people are talking of classification and regression trees, and people are also talking of techniques like random forests. I don't know if people are familiar with this term random forests, but random forest again is nothing but a special case of these carts, classification and regression trees. These are all essentially nothing but regression. So I have come to the end of my presentation today. And before I talk about some of the programs that I offer, I would like to know if anybody would like to ask any questions. I think we have done fairly well for time. We have just overshot by 5 minutes, but then we started 7 minutes late. So I think we're okay. Yes. Would you like to chat? I think it will be better if people chat and ask me the question. I can answer only. Thank you very much, Dia. Thank you very much. And thanks to all of you who have stayed awake. I know 4 to 6 is a very difficult time. At least I always fall asleep. Normally, I always take a nap. But because
Thank
today
you,
I am the
Ramdas.
speaker,
I
I could
think
take a nap.
it was a good refresher for me, having been stepped away from the academics and of course marketing campaigns. We do
Who is
use.
speaking? Is it Soumya?
Yes, it's Soumya here. So it
Okay.
was really a good refresher for me, and I think a wonderful session, I must say. We did issue a feedback form on the chat window, so if people would like to give feedback, please do fill out the form so that we can share with Ramdas. If you have any questions, please do type in the chat window, or you can unmute yourself and ask the question.
Okay, Anushree has been very kind enough to say thank you so much. Okay, it's I should actually like to thank all of you for having stayed awake during the entire proceedings.
No, not just
I
awake. I think they were very engaged as well. I saw a lot of
Yes,
engagement
yes,
actually.
I was very pleasantly surprised when I found a lot of answers in the chat window. I was very pleasantly surprised.
And by the way, everybody knew Kalpana Chawla, and it's
Kalpana
in the
Chawla
chat
again, but that was the second disaster, the first disaster. So it shows that people just don't learn. Of course, I have not gone into the reasons of the second disaster, but the first one, the Challenger, was when I was growing up. It kind of left everybody stunned actually. 73 seconds into the flight, it crashed.
Yeah. So no,
And oh,
I
by the way, this is again a topic close to my heart. I'm sorry for boring people like this. Just one more point. Now, I don't know if people have heard of a man called Richard Feynman. Anybody wants to chat, those of you who are still around, Richard Feynman, anybody has heard of Richard Feynman? Just say yes or no. Anyone?
I haven't.
Okay,
No.
Soumya says no. Dia says no. So that's 2 no's. Anybody say yes? Just to make me happy. I'm not going to ask you too many questions. Maybe somebody can say yes. No, Anushri also says no. It doesn't look like Feynman is a very popular character. Actually, Feynman as a person who many scientists, at least I would like to think of myself as one because I did work in these areas a long time ago. Feynman is actually the most colorful and famous physicist after Einstein. A very, very celebrated man, very celebrated. And there's a book which he wrote, which I recommend to everybody. And the name of the book is Surely You Are Joking, Mr. Feynman. It's a very humorous account of, it's an autobiography, it's a semi-autobiographical book where he talks about his life, like in addition to being a Nobel laureate, he was also a safe breaker. He used to break people's safes. In those days, people would keep safes in the office, to keep money and others. He was an expert safe breaker, lock breaker, and he also used to go and play the pongo at some of the local clubs. I mean, he was an absolutely colorful character, but he was actually fairly old at that time. He was the man who actually demonstrated on TV to the entire global audience the failure of the O-rings. There is a talk given by Professor Richard Feynman on this topic. So those of you who are interested, you can also actually read it. You can also listen to it. Today, most of us don't like to read. We prefer to listen. So that's just aside.
Podcast.
Anybody else? Anybody wants to add anything?
Yeah. I don't see any commentary
Okay,
on
I
the
think
chat
people are
window.
thankful that the damn thing is over, so I think we can let them off.
Nothing like that. I think I stayed for
I
full
can
two
see that.
hours and 10 minutes. So I really, and maybe even more, setting up the Zoom. So I think next time we'll
Yeah, and
sort
it
of
is really surprising why I was not able to share from my machine. It's really surprising.
No, no worries. We will probably set up another demo session with you, Ramdas. I think, but
Ah,
wonderful. Thank you so much for sharing your insights with us, and we look forward to more exciting sessions from you.
yes, thank
And
you very
we will
much.
put
Thank
that
you.
out in the calendar as well for the individual chapters who've joined us. Dr.
Your
Samiksha
voice
is
is getting
here.
distorted.
No,
Okay.
can you hear me now? Can you hear me now?
Yes.
Okay, no, I said Dr.
Yeah, I can
Samiksha is
hear you
here.
now.
Yeah, she's representing Christ. So, Dr. Samiksha, would you like to share
Yes,
any
I know she did.
thoughts? You'll have to unmute yourself and speak. I see only Dr. Samiksha here from Christ. Maybe Dr. Leja, would you like to share anything? Yes, Dr. Samiksha, we can see you.
I can
But,
see Samiksha on the window. I can see her.
but she's on mute and we can't hear her. I think she has to be unmuted. So maybe, okay, let's see who can unmute her.
Post. Yes, thank you, Soumya ma'am. So, Ramdas sir, it was really a very engaging session for all of us. Few of our students also joined. I think we will look forward for more such engaging sessions from you and learn statistics, because even for me, it's like quite a long time I touched the statistics. But again, to teach our data science student, I am also brushing up all the concepts.
Good. I'm happy to hear that.
Thank you, sir. It was
Thank
wonderful
you very much.
session.
Thank you very much. It's a great pleasure. I think we can keep on thanking each other. Most of the guys will probably leave by this time. So if
Yeah.
nobody has, anybody else here wants to say anything, or maybe we can leave shortly now.
Yes, we can. We can close the session.